Okay, welcome everybody. And it's my pleasure to announce my colleague José Caballero from the Centro de Astrobiología in Spain. José is mostly interested in exoplanets, um, brown dwarfs, also he's working quite a lot with instrumentation, and he has played a major role in the design, construction, and exploitation of the Caminus mission. So he has also some background in stellar multiplicity and astrophysical parameters. Mostly, people will know Jose from the last Beacon, where he presented a very successful planetarium movie, which has won several awards called Dark Biospheres. And he was also our chief technical wizard during the meeting, which I'm very grateful for, taking a lot of burden on my work. So that's enough, I think, from me. Welcome, Jose, and welcome you all. And the floor is yours for the seminar.
Hola y saludos a todos. Hi to everybody. Now you should see it in full. Okay. Now let's start towards inhabited habitable planets. Let's see this title by myself, José Caballero, at the Spanish Centro de Astrobiología, Center of Astrobiology. Let's let's start with a video that I helped preparing. It's in Spanish, but I will read it in English. Discovering an exoplanet capable of supporting life implies being within the habitable zone H of its star. This is Proxima Centauri b, of course, an artistic impression. The H is the region around a star that allows the existence of an exoplanet with liquid water on its surface. Here you have the habitable zone, and there you are either too hot or too cold. Beyond these limits, we will only find worlds of ice and steam. This is a world of ice, microlensing planet, and this is a world of steam, or rather a desert planet. This zone varies enormously depending on the size of the star, from the smallest, longest-lived and most stable stars, for example around M dwarfs, to the brightest and most massive ones, for example F stars. Billions of exoplanets located in habitable zones are waiting to be discovered. Okay, now you know what is habitable, and then in the title it was also inhabited. Inhabited is the past tense of the past participle of the verb inhabit, which means to live or occupy, and it comes from Latin habere, and it just means that there can be some living organisms there. Merriam-Webster provides some examples. The first one is the one that we are looking for, but I learned something about Spain, my country, that I didn't know, that Tabarca is Spain's smallest permanently inhabited island and has more cats than people. But of course, we are more interested in this. These inhabited planets and those signatures. But what are those signatures? Those signatures, I already talked on them on the EAI Academy a few years ago, and then you can get the YouTube video on exoplanet biomarkers or exoplanet biosignatures. and I was with a mask because maybe you remember something called COVID-19. Let's start now that we know what is the title, and I will start from the end. This is the end. This is what we want to detect. Inhabited planet in a habitable zone. Actually, we will see something like this. And here I am showing two spectra of the same object, which is an Earth twin observed with HWO and live at exactly 10 parsecs. These are simulations by Eleonora Alei that she made without noise and with noise. These are the spectra that the Earth would have, and there we would be able to detect such signatures. But for that, we need to know, we need to walk a very long track to reach these spectra. How can we arrive to those spectra? In May 2021, the European Space Agency published the final recommendation from the Voyage 2050 Senior Committee. It's like the NASA Decadal Survey, but for Europe. Before Voyage 2050 was the ESA's Cosmic Vision. Voyage 2050 had three main topics. One of them was from temperate exoplanets to the Milky Way. The other was icy moons, and the other was multi-wavelength astrophysics. And the senior committee said that the first option is a mission on the characterization of temperate exoplanets to have a higher scientific priority. That is life. And in a while, we will see what is life. That is plan A, but there is a plan B. If the technology is not mature enough, then ESA should focus on a galactic exosystem with astrometry in the near infrared. That is Gaia NIR. Step by step. In this Voyage 2050, there was also some paragraph on the contributions to the NASA Next Generation observatories. At that time, in 2021, there were Louvois, Habex, Lynx, and Origins. And in particular, it was Louvois. That it's something that, especially an instrument in the ultraviolet, could go to one of these NASA Next Generation observatories. Again, I insist, I will explain all these different terminology in the following slides, but I want you to know that I am starting from the basic principles of ESA's official documents. This is almost official because there was the interministerial meeting last November, and this is not exactly the final outcome because the increase that it is that you can see from 2025 to 2035, it does not have a slope of 4.5%, but only of 3.5%. But more or less is the same as it is now. And you can see from the bottom left, missions in nominal and extended operations, just to Jupiter, Euclid Cosmology, Bepi Colombo to Mercury, Solar Orbiter Heliophysics, James Webb Space Telescope. Then missions that will soon be launched. Plato, early next year, Ariel 2031, SMILE, Comet Interceptor. Then it comes LISA gravitational waves and visions to Venus, Arrakis, Neothena. Okay, M7, which is being selected right now together with F3. Look at L4. L4 is the mission to Enceladus of great astrobiological interest. You see the next one, L5, that banana-like place, that is the funding where part of the mission to this large interferometer for exoplanets, this answer to temperate planets for voyage 2050 would come. The study may start in 2028 with adoption and start of building things in 2039. So we are thinking of launching beyond 2045. And at the bottom, you saw this blue NASA participation. It's like the shape of a high velocity train. There can be the European contributions to the next generation observatory, in particular, Habitable Worlds Observatory. I mentioned before the plan B for the L5 mission. It could be the Gaia-NIR mission, which is just the mission Gaia, which maybe half of you know what is it. It made a 3D map, actually a 6D, because it has also velocities, 6D map of 1.6 billion stars in the galaxy, but instead of doing it in the optical, doing it in the near infrared. If you want to know more on Gaia-NIR, just ask me later and I can tell you. But we will focus on the important part for this seminar, which is exoplanets in habitable zones. And life is one of the first answers. Large interferometer for exoplanets. Interferometer because it shall make null interferometry. It will consist of 4 collector spacecrafts, more or less 4 telescopes of 2-3 meters each, with a fifth collecting spaceship, where the interferometry is performed and that sends the data to Earth, and would operate in the mid-infrared and would look for biosignatures in the mid-infrared around planets similar to Earth. You might think that this arrangement of 4+1 spacecrafts looks something more vintage like this. This is a picture of year 2000. This is Darwin, and is a concept of the end of the 90s. NASA has something similar called Terrestrial Planet Finder Interferometer. So it seems that we have not evolved a lot since then, but actually we have. This is a simulation by Philip Huber, when you can see how one could see, how life could see the solar system from 10 parsecs. And actually you could even see something on Mars, and life could be able to collect spectra of all these sources here. The European community is working hard on the LIFE initiative. For example, there was a meeting in Barcelona in November where around 200 astronomers, engineers, and some astrobiologists met to discuss how to proceed with LIFE and eventually go to the future. And there was a presentation by an ongoing current spacecraft that is flying right now above us. It is Proba 3, and it is a mission for heliophysics. but is that something relevant for life? Because it's doing flying formation, which is one of the technologies that would be a challenge for life. The requirement of Proba 3 was that it had a precision of 4.9 millimeters in a separation of 150 meters. However, the people of Proba 3 were very happy that they have improved the precision in the relative astrometry, in the relative precision between the two spacecraft, but 2 orders of magnitude, to 75 microns. And they have not turned on the laser, so they even can improve the relative precision. That would be enough for life to operate, although the collectors of life would be much more separated than 150 meters. So take note, LIFE, Large Interferometer for Exoplanets, the web page is LIFE Mission. And now let's move to the other side of the Atlantic. And again, this is a vintage slide with the NASA Great Observatories. And it is really vintage because they appear the old names of the missions. Compton Gamma Ray Observatory was the first NASA Great Observatories. It made some gamma ray observations. That it came Chandra, which is still flying, Hubble Space Telescope, which is still flying, and then it is written Sirtev, which actually changed its name to Spitzer, and Spitzer ran out of helium a long time ago already. These were the NASA Great Observatories launched between 1990 and 2003. Afterwards, the next great observatory was James Webb, which was actually a collaboration between NASA, ESA, and the Canadian Space Agency. It was launched in 2022. And I'm pretty sure that you know what James Webb can do, which is taking a lot of spectra of exoplanets, and what it cannot do, which is not taking spectra of exoplanets in habitable zone of 1 Earth mass and 10 parsecs. James Webb can observe big planets, but it needs a lot of time to detect atmospheres around the least massive planets in habitable zone that we are discovering right now. Well, James Webb is now flying, and then NASA started thinking on the following. In 2021, there were 4 proposals for next great observatory. I told you already, LUVOIR, that is Large Ultraviolet Optical Infrared Telescope, which is the one shown there, which is something like a big James Webb. Then HABEX, which means Habitable Exoplanets, Origins for Cosmology, and LINX, a Super Chandra, or in Europe we would say a Super XMM Newton. And in principle it should be launched sometime in mid-2030s. Things have changed. LUVOIR and HABEX merged into one project. Origins and LINX were discarded, and now NASA is focusing their interest in the next great observatory, which is Habitable Worlds Observatory, HWO, which, if everything goes well, will be launched sometime in the mid-2040s. This is an official slide made by Yada Arni. What is Habitable Worlds Observatory? A Super Hubble. Why it is a Super Hubble? Because it shall operate in the ultraviolet, in the optical, and in the near infrared. Remember, LIFE, the European counterpart, shall work in the mid-infrared. Habitable Worlds Observatory would work at shorter wavelengths. And at the bottom, you can see international contributions missions to be considered. Right now, HWO is 100% NASA, but it is publicly now that there are open discussions with ESA and Canadian Space Agency, as has been before, and even with the Japanese, with JAXA. What will habitable observatories be able to do? In principle, would be discovering biosignatures, robust real biosignatures on Earth twins. How will it do it? Currently, it has 4 ports for instruments. It must have a coronagraph. It must have a high-resolution imager. It may have a multi-object spectrograph, and there will be room for a 4th instrument to be defined. That may be the ESA contribution, which may be POLLUX. POLLUX is a high-resolution spectropolarimeter with which some of the people in the audience have been making already simulations of how we could be able to discriminate between an Earth with ice, with clouds, with surface, with oceans, with photosynthetic signatures, with ozone, everything that you can think of. NASA, during the last 2 years, have been working very hard on setting the stones for HWO and made the 4 main working groups: Science Community, Joint, and Technology. Europeans were allowed to work on Science Community and Joint, and it's everything that you can think of. I want to let you notice in technology, the 3rd block is written servicing. Servicing means that even HWO will be in Lagrange, in a Lagrange point. There will be some spacecrafts going there, like in Hubble, and changing the instrumentation. Remember, we changed instrumentation with Hubble, not anymore. We cannot change instrumentation with James Webb. With Habitable Worlds Observatory, we will be able to change instrumentation from time to time. This slide is written CAP participation in HWO. CAP means Centro de Astrobiología, but actually, except for the gray part, it could be also Caballero, Caballero, my name, because I'm involved in all these things in white, yellow, and orange. In yellow is that I was in charge of the selection of the committee, steering committee, and in orange was I was in co-charge of the group itself. And you may think that things have changed in the US with those executive orders for cutting the budget of NASA and so on. But NASA has been working very hard during these tough times. And they have made several architectural concepts. The one that it is appearing right now in the screen, it is one of the 3 that were prepared. There you can see a 6-meter telescope, primary with off-axis. The secondary is not in the middle of the optical axis, and everything is protected by against the micrometeorites. This is another architectural concept. Again, everything is covered, and this one I think it was 8 meters in size, and again it is also off axis. And there is a 3rd one which is on axis. These are the three that were presented in Washington in October last year, but there is a fourth architectural concept still to be released, but in a very advanced mode. Actually, on the 5th of January 26, and that is 1 month and 20 days ago, NASA gave $150 million to 7 big astronautical engineering companies. There you can see L3Harris, they made Hubble, Lockheed Martin, Northrop Grumman, British Aerospace, and they all are right now working on different technologies for HWO, plus another 30 million that NASA gave for moving the headquarters of HWO. In parallel, ESA is doing their homework too. Rather than ESA, the European community. And the European community will organize the next HWO meeting, and take note of the dates from November 30th to December 4th. It will be in Massy. It is in the south of Paris, very close to Paris-Orly. And I hope to see many of you there, those of you who want to detect biosignatures during your active career. In the meantime, I go on working on the characterization of the target list that HWO may be eventually observing. We have to characterize X-rays, multiplicity, absence of companions that can affect activity. That was life. Sorry, that was Habitable Worlds Observatory. But in Europe, we are doing the same for life. Life will also need a catalog. And you can think, why starting preparing a catalog 20 years before the mission? Well, you need to have a preliminary list of targets for defining the scientific requirements of the mission. So you need to know more or less what you are going to observe, or you must be more or less quite sure of what you are going to observe. Because if you are observing faintest stars or stars that are in multiple systems or whatever, maybe you will not need a telescope with a primary mirror of 6.5 meters, or you will not need a spatial resolution of 10 milliseconds. So you need the target list right now. Actually, we are starting working together, LIFE and HWO, for defining a kind of common target list, or at least sharing information for not duplicating work. And there you can see that it is LIFE, HWO, and Tianlin. Tianlin is the third exoplanet hunter that is planned to be on the sky, probably even before than HWO, maybe at the end of the 2030s. 6 meters, like Habitable Worlds Observatory, ultraviolet to optical, maybe some near infrared, because it will cover J and H bands, and it will have high dispersion spectrograph, high resolution camera, and of course the coronagraph. What is unique is that the main mirror, which would be 6.6 meters, would be monolithic. Instead of being made of segments like James Webb or HWO, it will be just one single piece of mirror. that was in space. And what about the Earth? And the Earth, that's a picture of last week. This is the 39-meter extremely large telescope from inside. This is the mount, and this is inside the dome. It is virtually done. It's on a schedule, and it will have a number of instruments. The first one will be Mikado. It's the simplest instrument because it will just make some imaging camera in a wide wavelength range. It will be fed by the Morpheo adaptive optics system, and already with Mikado we will start resolving Earth mass planets around the nearest stars. It will cover Y, J, H, and K, that is the optical and the near infrared, and it will have some moderate spectral resolution, so it will be able also to take spectroscopy apart from imaging, and a spectacular spatial resolution of 1.5 pixels. And that's really very small. METIS will be next, and we'll be observing in the mid-infrared, like live, beyond 5 microns. Actually, between 3 and 13 microns in imaging, and 3 and 5 microns in integral field unit spectroscopy, with modes at spectroscopic modes at very low and very high resolution. So you will have many different options to choose. Andes is very important, because Andes, for those of you who work in exoplanetology, is like a super HARPS, or rather like a super Carmenes, because in one shot it will cover in very high spectral resolution, more than 100,000, from the near ultraviolet to somewhere in the middle of the near infrared. We don't know yet if it will reach the H band or the K band, or at least it has not been made public. And the thing is that it will be extremely precise. While current instrumentation hardly goes below 1 meter per second in radial velocity, precision, and accuracy around the closest stars, Andes should be able to reach 10 centimeters per second, or the order of 1 order of magnitude better. And that will be able to see, to detect very low mass planets, but also to study the atmospheres of some of them that are transiting. And among other things, can even measure the acceleration of the universe expansion, which is something that it will be a Nobel Prize. And HARMONI, it will be a bit more complicated, that will come later, and will do a lot of things. Imaging, low resolution spectroscopy, high resolution spectroscopy in a lot of wavelengths. And there is another thing, because the ones that I showed you before are the ones that can do something related to exoplanets in the first and second generation of ELT instrumentation, but ESO is already thinking for what we sometimes call third generation of instrument, and it is PCS, planetary camera and spectrographs. With this, we will be able to take real spectra of planets, some of them similar to Earth, around the closest stars. And there you can see Proxima Centauri. That will be an easy target. The planets around Barnard star are also easy targets. Remember, Proxima Centauri b is in the habitable zone. And this is a summary of the table of the different instrumentation for the ELT. Mikado Morpheo is the adapted optics module that will inject light for Mikado and very likely HARMONI. MET is in the mid-infrared, and there's the high-resolution spectrograph, and Mosaic, which will be mostly used for extragalactic science, plus this PCS in the future. And this is ELT, and ELT is moving already, as you can see. So the dome is being finalized, and in a couple of years we will have the first light. And you can think, and especially those that are watching this video recorded, what about the American large telescopes, the GMT and the TMT? Well, I can say that GMT has made a lot of things, started building in the site, have a lot of components, including casting the 7 primary mirrors and polishing some of them and making a structure, and the main tank of one of the instruments, G-clef, plus the telescope mirror actuators. But this is what Dan Jeff, sorry if I pronounce it incorrectly, who is the new GMT president. All 7 mirrors that are needed for the telescope are cast, and a number of them are already finished. Whoever, they have more or less 50% of the money to finish the telescope. So it will take some time until GMT is finished. And what about TMT? Well, TMT has been stacked for a long time. The latest news were that Spain would provide 400 million euros if it is eventually located in La Palma instead on the summit of Mauna Kea. It is true that Mauna Kea is at 450 meters and that La Palma is at 2,350 meters. It is a difference of 2 kilometers, and the quality of the astronomical observations is obvious that it is much better in Hawaii. But it is the difference between making the telescope and not making the telescope. So now our US colleagues should seriously consider the invitation of the Ministry of Science of Spain for coming to La Palma. And this is the previous to the last slide. I am asking you, when and how will you detect the first incontrovertible set of biosignatures in an atmosphere on an exoplanet? And I say you because it will be you, it will not be me, because I may be alive, but certainly I will not be, I will be retired by that time. So this is a summary with some estimated dates that I wrote. You have the ELT instruments will come first, Mikado, Metis, Andes. HARMONI and GMT will come next, then PCS, maybe TMT, first in the space the Chinese with Tianlin, Habitable Worlds Observatory, and Life. And in different colors are how closer or how much close we are to real robust biosignatures. I hope that the combination of HWO and Life will be the final combination of all of them. But PCS and Tianlin or even Andes could give us a very good surprise before that. This is just one scenario. There are different scenarios. This is if Gaia Near is an M9 or M10 mission, but things might change drastically from which I am showing you, especially before 2040. What we have to do from now on, working together. We are working the Europeans, we are working the Americans, the Chinese, and why not the Africans, the rest of the ASEANs and Oceanians. We all want to detect another Earth around another star. Why not really working together, saving money, maximizing synergies, minimizing overlapping and duplications? So come on, let's work together. That's all. Thank you very much.
So, thank you. Yeah, okay. So I think we can now open for questions and discussions. You can ask questions by raising your hand, and also you can ask questions on the chat. And we have the first question here by Giuseppe Morante.
Ciao Giuseppe.
Hola, José, ¿cómo estás?
Ciao.
Tengo dos preguntas. I have two questions.
In English, in English.
Yeah, I have two questions. The first one, what about the golden sample of Andes on EELT? So there are other exoplanets in the habitable zone and outside the habitable zone that are selected for being investigated by Andes, no?
Yes, I may answer first this. I will explain what is this. Andes will do high resolution spectroscopy like HARPS and so on. And there is a paper by Enrique Paget et al. In which he showed a list of, I think it was 7 planets around more or less the 7 closest stars with exoplanets, because ELT will be able to resolve the star and the planet. So Andes will be able to take a spectrum of the planet themselves. That list has been recently updated by Julia, who is a research fellow here at ESA, and has added one more. These are the golden targets for Andes, but it does not mean that they will be the golden targets for the rest of the missions. Personally, I think that it is a very good choice, but there are pros and cons. For starting, I like it's a very good sample. If you want to do detail for a specific instrument, then you have to start thinking about those small details. And the second?
Thank you. And the second is, what do you think is an incontrovertible biosignature? For instance, a technosignature would be quite incontrovertible.
Yes, but I am thinking more of what, for example, Ed Schwitterman would say. There is a very good team of biosignatures scientists on the other side of the US, of the Atlantic in the US. I have been working with them with this thing of the HWO. And for me, it's a combination of a number of molecules that satisfy oxidation and reduction together, out of equilibrium, presence of oxygen indirectly from ozone. So you will be kind of a combination of ozone, water, CO2, methane, plus another 2 or 3 that Ed Schwitterman should tell you better than me. There are some papers on this. I will write again. Peterman. I think maybe it has two T's. It is in the chat. I recommend you to look at his papers because they are very comprehensive, and there you can see a lot of potential robust incontrovertible biosignatures. Bill?
Thank you.
Bill?
Yes. American astronomers are quite constrained in the ability to interact with the Chinese. Is it easier for Europeans?
Okay. I will show you again this where this slide. There you can see Natalie Hinkle. She's from the US, and the other are Europeans, and there is only one Chinese. Of course, it took me ages to get people on board. We Europeans, we do not have any problem at all, any restriction at all, or working with the Chinese. Americans in general, except for those that are in some relatively free universities and so on, they cannot work with Chinese, even if they were publishing together just last year, which is the actual case. So it does not apply to past projects, but to new projects. And this is a new project. So what we agreed is that I would make as a bridge between the European and Chinese community on one side and European and American communities on one side. I hope that eventually this thing will change. For the moment, Europe, and in particular Spain, as Europeans will go on working with both NASA mainly, but sometimes also with China for specific projects. Actually, just to finish, China is building a new spectrograph for the 10-meter telescope, Gran Telescopio Canarias, the GTC, which is in La Palma, is the largest optical near-infrared telescope, bigger than bigger than Keck. And China will put this espresso-like instrument on the telescope, and they will be given 5% of the telescope time in exchange. So Spain and China will be soon even working more and more closely.
That's very good. Yeah. We hope things will change in the US.
Eventually, I think that it will. Good luck, Bill. Good luck.
Thank you.